To start, the idea is to take around 30 minutes for this part of a lecture about coal, and so that we have the time for 15 minutes break, and then move to the following lecture, 45 minutes about nuclear. So as Stefano introduced, I'm Francesco Baldi, and I'm also part of the lab, and I will be talking about the bad guys in the energy conversion universe, so coal and nuclear. The way I structure my lectures are pretty much the same for both, more or less. So a first introductory part in which we really go down to what is really important, let's say, about these types of energy technologies. So why, what is coal energy? What are the main characteristics? Why it is good and why it is bad? And then we will move to a bit more into how it actually works. So how it works to burn coal and what is the thermodynamic cycle behind it. We'll look a bit into the environment because as we will see later, the environmental concerns related to coal is one of the main reasons why we should not look too much into coal. And then we will have a brief overview of what are the future technologies that will hopefully make coal a bit better and that are coming in the few years to come. But so to start, just as an idea, today 40% of the electricity globally is produced by burning coal. So coal is quite an important mean for energy production today. I put a quantification, it's 160 quadrillion BTU. It's not easy to say what it matters, what it means in practice, but I would say that is a lot. Luckily, coal is not expanding. We are seeing that in some countries, particularly in Europe, and in general in countries like US and so on, we are phasing out slowly coal. But on the other side, in growing economies, coal is becoming more and more important. So the overall trend is more or less constant. We see already down here one of the reasons why coal is is still there. It's because there is a lot of it. The total duration expected for the coal reserves today is for almost 200 years, and there are some parts of the world in which it is even longer, of course. When we look at the situation in Europe, we see that it's very variable, but there are some countries, typically those countries that have a lot of coal reserves, like Poland and Germany and Czech Republic, that rely heavily still on coal power production. So why coal energy? Well, we said it a bit already. Probably the main reason is that coal is cheap. It's been, and it is still today, very cheap to produce energy using coal. As a matter of fact, regardless of what are our convictions related to environmental impact and so on, many times it boils down to use the cheapest option, and that's why coal is still there a lot. One other reason, it's a bit more interesting, I would say, is that it is very widespread around. There are many countries who can rely on their own coal reserves. And that politically is a strong point, for example, differently from natural gas or oil that are located in some specific parts of the world, and not necessarily in those ones that are the most stable. Coal is available, as you can see here on the map, coal is available a bit everywhere. Well, furthermore, coal, we will see later the power plants, but coal has been used for years, for many years, and we know that it works. When it comes to the why not, well, the main reasons are related to its impact on the environment. So yes, as we said, we said that there is a lot of coal left. Still, it's a fossil resource, so it means that one day it will end, which in itself still says, okay, we can still use it, but we should, at a certain point, get rid of it. And then the main issues are related to CO2 emissions. As you can see from the table here, every burning 1 kilogram, getting one gigajoule of energy from coal generates between 80 and 100 kilograms of CO2. While, for example, natural gas, which is still a fossil resource, only generates 56. And of course, we are still in generating CO2, emitting CO2 anyway. That is a big problem, as all of you, I guess, know. And with coal, particularly, we have a lot of other problems related to other pollutants, nitrogen oxides, sulfur oxides, and particulate matter in particular. We will see them a little bit later, and the reason why we see them for coal power plants is because coal, among all energy sources for electricity production, is the one that has the most problem related to these other pollutants. So, how does a coal power plant work? In itself, it's pretty simple. You have already seen the Rankine cycle, and it is exactly what we have as the basic thermodynamic cycle for this type of power plants. The type of plant, well, from the coal storage, we have like a furnace where the coal is burned and generates the heat that is then transferred to a heat transfer fluid that normally is steam. And then simply the steam goes through a turbine that, where it expands, generating first mechanical power that is then converted to electricity. The water is condensed, pumped again, and the whole thing starts over. So nothing strange here. We will not go much into the properties of a coal, how a coal like a furnace works. It's there again. There will be in principle a lot of knowledge behind, but in practice, what we need to know is that they are very big things. And what we normally do in the traditional power plants today is that we inject coal in powder form, so well, kind of dust. So it's very fine. Which in itself needs, for example, very dry coal, because it first has to be grinded and then it is blown into the combustion chamber. We have different configurations, but the idea is always the same. It is blown inside. There are some, basically with the fire that is already there because there is already things burning, they basically are transported away through the furnace, and in this time, in this short residence time, these small particles of coal, they burn. And by burning, they release the energy that we need. The heat that is generated during the combustion, it is normally transferred in two main ways. So this whole furnace is normally surrounded by pipes with water and steam flowing inside. So the heat that is radiating directly from the combustion goes to the steam, to the water on the outside, and generates and makes it like the boiling from water to steam. Then we have the exhaust gas that are leaving the combustion area that are still very hot. They go through a battery of heat exchangers that are located up there normally. That normally are the economizer and the superheater, so the coldest and the hottest of the heat exchangers. As we said, when it comes to the thermodynamic cycle behind, it is a Rankine cycle. It is not the most simple one. As you have seen in the lectures before, the simplest version of the Rankine cycle, which is simply basically like evaporating once and then expanding, can be improved in terms of efficiency by a number of measures. And since here, as we will see a bit at the end of the lecture, in coal power plants, the cost of buying the fuel is one of the most important during the operational life of a plant. We want to make the plant efficient. So all those possible means that we have to make the thermodynamic cycle more efficient when we use them. So for example, in this type of power plants, we have, well, not only superheated steam that of course is needed for efficiency, but also for the integrity of the turbine. We have reheating, so as you can see here, the steam is first expanded at intermediate pressure and then heated again at high temperature and then expanded again. And then we have the so-called bleeds, so where the steam here, part of the steam here is taken to preheat the water and steam on the other side. And in this, for example, in this figure, so in this thermodynamic cycle that is represented here, we have 2 levels of pressure and 1 bleed. In a real, like in a big real power plant, we can have up to 7 bleeds. So we have very many different stages in which the different intermediate cycles are connected. The plant becomes more complicated, but even 0.5%, 1% means a lot in these power plants. This means that today, So the average efficiency of the plants that we have in the world today is around 38%. If we were to build like a traditional power plant today, we would probably have a 42% efficiency, which is more or less the state of the art today, let's say. Okay, so that was the first part. Now we dig more into the, let's say, the bad aspects about coal, because so far we have said that it burns in the combustion chamber, it works pretty well, it has a decent efficiency, coal is cheap, fine. What is the problem then? There are three main emissions that we focus on when we talk about coal power plants. They are not the only ones, but they are the ones that are the most dangerous and the most important. It's sulfur oxides, nitrogen oxides, and particulate matter. And for all of them, during this 5 minutes of the lecture, we will see what is the formation mechanism. So how are they actually formed? What are the effects, both on the environment and on human health? And what are the ways to reduce these emissions? Okay, this is quite a heavy content slide. Still more questions. I hope you're happy with that. So the first one, sulfur oxides. Its formation mechanism is very simple. If there is sulfur in the fuel, that sulfur will become sulfur oxide at the end of the combustion, because sulfur prefers to be in its SO form. Most of its effects on the environment are, most of its negative effects are connected to the effects on the environment. We're talking about mostly acid air rain. So what happens is that the SO2, for example, in the air, it reacts with water and gets H2SO3, which is an acid, that then condenses with the rain and comes down. In its mildest form, it's gonna basically like consume marble monuments, which is kind of problem in the country where I'm from, in Italy, where many monuments are in marble and they are heavily damaged by acid rain. In general, they can basically melt down forests, they make the soil acid, so it's quite a bad effect on the environment, and it's one of the first ones that has been tried to take action on. In addition, in itself, it doesn't affect human health, but sulfur oxides can act as precursor for particulate matter formation. So basically what happens is that the sulfur oxides they are emitted in gas form, but then when the exhaust gas lower the temperature, they condense, and then other particles build on them. And that generates particulate matter, which, as we will see in the next part of the slide, is very bad for human health. So, sulfur oxides, bad. Second one, nitrogen oxides. This is a bit more different type of pollutant. Firstly, from where it originates, because most of it originates from nitrogen and oxygen in the air. And since we are always burning, when we burn something, we need air. Well, in principle, we just need oxygen. In practice, it's easier to take it from air. So we also have a lot of nitrogen around, and at high temperatures, so we're talking about above 1,500 degrees, we have a certain mechanism that is activated, and it starts generating a lot of nitrogen oxides. They can have very bad effects, especially on the environment. Particularly, again, it generates acid, so acid rain, but then water eutrophication. If you've not heard of it before, it means that nitrogen is a nutrient. So when it goes into the water, there are a lot of water plants, specifically algae, that tends to, at a certain point, start to grow, and basically they destroy everything else, because they outgrow all other living organisms. So water eutrophication is a big problem. Generally, the most important factor in eutrophication is connected to the use of fertilizers, but also nitrogen oxide emissions don't help. And then it damages plant growth in itself by clogging the way the leaves work. Nitrogen oxides have a more limited effect on human health, but so it has to be at high concentration. So, for example, if you are in the middle of a traffic and there are a lot of old cars, particularly diesel cars, then you might feel some effects out of nitrogen oxide. Finally, particulate matter. Particulate matter in itself, it originates from either incomplete combustion, so if you have like small particles that don't burn completely in the combustion chamber, or you have it when you have ashes, so something that is already in the fuel that basically can't burn. And that is typically from coal, but also, for example, from biomass, because there are like salts and stuff that if you ever done like a fire with your friends, what remains at the end, the ashes, are actually parts of the fire that of the wood that basically cannot burn. So that thing, when it's very small, becomes a problem. And it is mostly a problem for health. Particulate matter basically goes through our lungs when we breathe, and it was estimated in 2016 to generate 4.2 million deaths in the world. That's quite a lot. It's tricky to control because it's not only connected to the weight of particles, but mostly to the size. Smaller particles get really much inside and they create the most damage, and are also the ones that are the hardest to control. So particulate matter is really, really bad, particularly for human health. When it comes to the environment, it's a bit more tricky. Well, of course, in general, they're not really good. For the climate, they can have a warming or cooling effect depending on what type of particulate matter we're talking about and where we are. In general, they have a cooling effect, but for example, many particles that end up in the Arctic, then many of them are black by color, so they deposit on the ice, and then the ice and the snow tend to absorb more heat because it's black, so it generates a worse effect. So, a lot of bad stuff. How do we deal with it? First, sulfur oxides. There is one technology that is, well, in principle there are many, we don't have time, so we will talk about one that is the most common by far. It's basically a shower. It's, we wash the exhaust gas in a shower. So how does it work? Well, the water that we spray on the exhaust gas reacts with the exhaust gas themselves. And we don't just put water in this scrubber, we put water with basically dissolved in the water, normally limestone. What happens is the reaction that you see down here. So we have the limestone, which is calcium and a carbonate ion. And we have like basically the two ions switch. So you have that from CaCO3 plus SO2, you get CaSO3, that is basically gypsum. And you can collect it at the end, and CO2 on the outside. So this way of reducing emissions, of course, it works very well, and you have like a very high efficiency of reduction. You need a reactant, so you need limestone. You buy it, and in some cases you can even buy the product. So you can, sell the product. So gypsum can be sold for different uses, for construction material and so on. Nitrogen oxides. In this case, in principle, it sounds to be easier because in nitrogen and oxygen prefer in normal conditions to be on their own. So they prefer to be in form of N2 and O2. In practice, this will be very slow, too slow for our taste. So we need two things to make we need three things to make them go back to the original form. One of them is ammonia, because we don't just let NO to separate on its own. We provide something to generate the reaction that we're interested in, and you can see that there. This reaction needs temperature, so it can only happen at relatively high temperature, and it is only fast enough at the temperatures that we have if we use a catalyst. That's why these components that are with systems that are called SCR, because it's selective catalytic reduction. The reduction is because it is the opposite of an oxidation, so the type of reaction is a reduction. And catalytic because we have a catalyst in there. The tricky part is that it has to be at high temperature, so we cannot put it wherever on the exhaust gas. We have to put it in a point where the exhaust gas are still sufficiently high for this to happen. Last but not least, particulate matter. Here one could spend hours talking about how to reduce particulate matter emissions. we normally have three main strategies. One of them is to simply use the fact that they are heavier. So we use a separation system based on inertia. Typically, this kind of cyclones, they make the exhaust gas to rotate. And by rotating, the particles that have more inertia, they tend to stay on the outside. And then you just take the stuff that comes out from the outside, and that's particulate matter. Then we also have the fact that many of these particles at high temperature, they become electrically charged. So we just make them go through an electric field. And they will basically be attracted to the two sides, depending on how they are charged. And then we just scrap it out. And finally, we have fabric filters that are just like giant socks. The exhaust gas go through them, and it basically gets stuck. It's very simple to understand. The thing that is a bit more interesting is that the filter itself, so the filter bag, it's not what really does the filtering. What does the filtering is the layer of particulate matter that gets stuck on it. So when the filter is clean, it doesn't really, as crazy as it might sound, it doesn't work very well. It works best when it has already been used for a while, so there is like a layer of particles of particulate matter that is stuck there, that is doing the filtering. In practice, what we will have is that we will have all of these ones combined. So normally we will have in the beginning a cyclone to take away the largest particles, like the big bunch of particulate matter. Then we have an SCR that is there for reducing nitrogen oxides at high when the exhaust gas is still at high temperature. Then we have the other more effective particulate matter reduction, so either fabric filter or electric separation. And then in the end, the scrubber, which is at the very end because it humidifies the air, so it's like really the last thing that you want to do. Okay, the last part of the lecture, alternative coal-based power plants. So the new ones, let's say, so the ones that are what we are using to do clean coal, as Donald says. The first one is a rather simple concept. It's just basically taking the existing ones, don't change anything, but making them more efficient. To do this, well, the thing is that in the combustion chamber, actually here, you have very high temperatures. So if we talk about a normal Rankine cycle with, let's say, maximum pressures of 160 bar, a maximum temperature of 540 degrees, we can do better than that. Up to the point in which we go to we have like a supercritical steam, so like we go beyond the critical temperature and pressure of steam, of water, and we really push up the pressure, so we see that if this is already quite a high pressure cycle, this one becomes a really high pressure, 320 bar is really a lot, but that means that by having higher pressure and higher temperature, and also by having a more smooth heat exchange profile, we can go up to 50% efficiency. The second way is fluidized bed combustion. If you remember, John Oliver said it before, like in the list of things that Donald Trump is supposedly expert in. The idea here is that we change the way we do the combustion. We don't go into the details of how it works, but you have to imagine that we, instead of like having the very fine coal that goes in and then it's basically quickly burned by flowing through the combustion chamber, here we have like big pieces, big chunks that go in some sort of this fluidized bed, which is something that bubbles around, stays there, and it stays on this kind of gaseous grill until it's burned to be small enough that the air that is blowing from the bottom and that is creating this kind of bubbling bed and basically pushes the small part that is remaining out. Why do we do this? There are some reasons. Well, then the rest is very similar to what we have in a normal power plant. The only thing is that in the fluidized bed, we don't only have fuel, we normally have other things, particularly some sand that is there to increase the heat transfer, and that is just put back and recirculated. So, what is the point here? First of all, In this type of system, the combustion temperature is kept low because of because of the sand, because how it is designed. And by having a low temperature, you basically don't allow the temperatures that are required to generate NOx emissions. So you don't need an SCR. You just have basically you don't generate NOx. Since we said that we have this kind of sand in between, you can put also limestone directly in the combustion chamber. The limestone will directly react with sulfur. So basically you don't need to put a scrubber at the end because the solid oxides are eliminated directly in the combustion chamber. Finally, since I said that in this case you can have larger pieces because they stay there until they are consumed. It's, in this case, it's easy to burn like a bad quality coal. So like the coal that is more humid, they're difficult to actually make into powder, and even can allow co-combustion with biomass. So in this case, you can easily have, for example, 50% biomass and 50% coal. In general, the problem is that these systems are a little bit more expensive and less efficient and more difficult to operate and control. The last one is basically the idea is that we, in this, according to integrated gasification plants, we don't burn coal anymore. We take the coal and we gasify it. When we gasify, it means that we take the coal, we let it stay at high temperature in presence of other agents, particularly steam, and the temperature the high temperature that is generated by burning some of the coal will make the lightest part of the coal to be released, and by reacting with the steam, it will generate a mixture, a gas mixture that is made of CO, H2, CO2, and H2O. So like water, carbon dioxide, carbon monoxide, and hydrogen. That is normally very easy to filter out and to separate into different from the rest. So the control of the pollutants happen before combustion, and then we have a clean gas that we can use either in a combined cycle, so with like a gas turbine and then a steam turbine, or even in a fuel cell. With the idea that with this system, with this type of system, we get very efficient and with quite a clean system. Also, and probably it's the most interesting thing of this type of systems, to capture CO2 is easier and cheaper when you do gasification first. You will have a lecture about carbon capture and storage. As we said, that one of the main problems of coal is CO2 emissions. The fact of saying, look, we can separate CO2 and collect it somewhere easier with this type of systems, it's a big point forward, especially looking into the future. As you see here, this is an estimation that I took from a report from the MIT that says that if integrated gasification is 5% more expensive than normal pulverized coal power plants, when we look at a system with carbon capture that already becomes very quickly much more expensive, then the standard system is 60% more efficient than the no carbon capture one, but the IGCC is only 30%, 35% more expensive. Last thing, as Stefan introduced before, you will have this project to work with starting from next week, if I remember correctly. And in this project, we will have to introduce technologies based on a number of their features, and the ones for coal are summarized in this slide. So you will have the slides available. So just to let you know that this is there. So to conclude the lecture, coal is dirty. We know it. On the other hand, we know that it is here, and it is here to stay for a while, because it is a known technology, because it's cheap, and because there's a lot of it. So we said coal has a lot of negative consequences on the environment and on human health, particularly because nitrogen oxides, sulfur oxides, and particulate matter and CO2. But there are some things that we can do to at least mitigate these effects, and we have seen all the different components that are used and can be used. And finally, we went through quickly a couple of new technological developments that can maybe bring some of the solution, particularly very high pressure and temperature, so ultrasupercritical Rankine cycles, fluidized bed combustions, and integrated gasification. Bottom line, coal is bad, but could be worse. Okay, so this is done for the coal lectures. I hope that they are happy to have a short break. So we start again at 12.